My name is Mohammad Ghanatian, and I'm going to talk about dynamic modeling, parameter identification, and nonlinear model predictive control of a cable suspended parallel robot with four cables. This is the work that's been done in collaboration with Professor Mohammad Yazdi and Professor Mehdi Taleb Masouleh at Human and Robot Interaction Laboratory, University of Tehran. At first, I'm going to talk about cable suspended parallel robots or CSBRs. This is actually the cable suspended parallel robot in the Human and Robot Interaction Laboratory. And as you can see, it has four motors and an end effector, and the end effector is connected to the motors using flexible cables, and the rotation of motors moves the end effector in the workspace of the robot. These robots have many applications, but probably the most famous one is Skycam, which is mainly utilized for video capturing of football games. Other applications consist rehabilitation, pick and place, or even 3D model reconstruction of objects. In this slide, I'm going to talk a little bit about model predictive control. This figure shows the concept behind MPC in a simple way. And this red curve is the reference trajectory. And this yellowish line is the predicted output of the system. And we want to minimize the difference between these two curves in our prediction horizon by finding the optimum value of the control signal in our control horizon. These controllers, they have many merits and drawbacks, but probably the most famous ones are regarding the advantages. These controllers are able to control multivariable systems, and also they can handle constraints. And regarding the disadvantages, in these controllers, we require a model of the system to design the controller. And also, these controllers can possibly have a huge amount of computational cost. In this slide, I'm going to talk why we decided to use a nonlinear MPC for controlling CSBRs. Using MPC, we can minimize the controller error and the controller signal simultaneously. And in controlling CSBRs, there are many constraints that we can implement them. We can easily consider them in MPCs. These constraints could be the tension in cables, which should always be positive because cables can only be in tension and not in compression. The amount of control signal should be less than the maximum amount of torque each motor can exert. And the output of the system, I mean the position of the end effector, should always be inside the workspace of the robot. And regarding the reason why we decided to use nonlinear MPC rather than linear MPC, I've got to say that because of the fact that the dynamic model of our system is nonlinear, if we wanted to use linear MPC, we had to linearize our dynamic model around an equilibrium point, for example. And in that case, we could only control the system around that point, and we couldn't use that for an arbitrary input signal. In a previous slide, I mentioned that we require the dynamic model of our system in MPC, and because of that, in this research, we actually utilize Newton-Euler method to drive the dynamic model of our robots. At first, we drive the dynamic model of the winches of the robot and the end effector. And then we combine these equations together to obtain the dynamic model of the robot as a whole. And then we utilized Simscape environment of MATLAB for verifying these equations. Of course, we modeled the physical system of the robot, and then we gave this random white noise torque to both of these models, and we observed the output joint angle outputs. And we realized that these two signals, these two outputs, are lying on each other for all the four motors. And of course, the maximum amount of error was about a quarter of a radian, while the range for the output was about 40 radians. And we realized that in the dynamic model of the system, there are two parameters that could be changed over time, and these two parameters are the mass of the end effector, m, and the friction coefficient of the winches, Fv. At first, for verifying these two parameters, we discretized the dynamic model of the system using Euler's method, and then we generated some input-output data pairs for 3 cases with different M and Fv parameters. And after that, we converted the identification problem into an optimization problem. We considered M and Fv as our design variables, and we wanted to minimize the difference between the response of the dynamic model and the output data that we obtained from the Simscape model. And of course, we consider some constraints on these two, I mean the Fv and M parameters, because they should have some logical values. And then we utilized the genetic algorithm with a population size of 500, and in 10 generations we achieved these results. And as you can see, the average amount of identification error for identifying the M parameter was about 1.25%, and the average amount of identification error for identifying the Fv parameter was about 0.33%. In this slide, I'm going to talk a little bit, about the structure of the nonlinear MPC that we designed. And this is the optimization problem that should be solved in each and every time step. And it has a cost function that captures both the controller error and the controller signal. I mean a lambda fraction of the controller signal. And regarding the constraints, the first constraint that should be considered is the dynamic model of the robot, I mean the discretized one, which should be followed by the system. The other constraint is the tension in cables, which should be always positive and less than the maximum allowable tension that could be applied to each cable. The amount of control signal should be always less than the maximum amount of torque that each motor can exert, and the output of the system, I mean the position of the end effector, should be always inside the workspace of the robot. We ran this algorithm in two scenarios. Once when the precise parameters were utilized in the model of the MPC, and once when the identified parameters were utilized in the controller. And we made many efforts to do this computation, to solve this optimization problem in real time. And these efforts include assigning the value of 3 to both the prediction and control horizons. The sampling time was 0.1 seconds, and the optimization method was interior point and with a maximum iteration of 15, and the Core i7-4710HQ CPU was utilized as our hardware. And and then we assess the performance of our controller, we considered the this reference trajectory, and we observed the amount of controller error for all the three cases. You can see that in these 6 plots, the amount of error for all the three cases are plotted when the precise and the identified parameters are utilized in the MPC model. Also, we calculated the amount of RMSE for all these 6 scenarios, and as you can see, the average amount of RMSE is about 3.5 to the power of -4 when the precise parameters are utilized in the model, and it is increased to 1.1 to the power of -3 when the identified parameters are utilized. As a result, in this research, we illustrated the promising performance of nonlinear MPC for controlling CSBRs when they are combined with the identification method that we utilized in this research. This is due to the fact that not only the average amount of error in identifying both the M and FV parameters are promising, but also the amount of control RMSE was satisfying when the precise and the identified parameters were utilized in the model of our controller. Moreover, this controller can be utilized for tracking any input signal as long as that's in the workspace of the robot, because we didn't linearize the nonlinear equation of the robot around an equilibrium point or anything. Regarding the future work, we aim to experimentally implement this strategy on the CSBR in the human and robot interaction lab, and we aim to reduce the sampling time of our controller by coding this controller in a much faster programming language like C or C++ rather than MATLAB that we used in this research. And we are also going to use more advanced techniques for discretizing the dynamic model of the robot, because the Euler's method that we use in this research is not that much successful when there is noise. And yeah, that's about it. Thank you for your attention.